that will be sampled. It is continuous in frequency domain, continuous function, but we will sample it over one frequency cycle 2 pi. Okay. Now, over this frequency cycle 2 pi, if we take the uniformly distributed samples, then if you calculate the inverse discrete Fourier transform, okay, then we can find out the Hn from H omega. H omega is the frequency response, frequency domain representation, and Hn is the time domain representation. So Hn you will get for finite set of values. Okay, let us say from 0 to m minus 1. Okay. Now, the set of sample points used in this procedure can be determined by sampling a desired frequency response Hd omega at m points 0, 1, m minus 1. So I have given one notes regarding this, like say this is your desired frequency response, that is blue line, okay, over the frequency range 0 to 2 pi. So we'll sample it, okay. Uniformly we'll sample it. Say let us say we sample it for 18 number of points. So there will be 0 to 17 will be the sequence. Okay. So this is one structure. Now magnitude frequency response is symmetric about pi. Obviously it is actually minus pi to pi or 0 to 2 pi, minus pi to pi or 0 to 2 pi. Okay, so 0 to 2 pi or minus pi to pi, it is same thing, but it is shifted in the positive frequency side. Okay, so from at the middle of the center of symmetry, that is pi, at omega is equal to pi, they will be repeated. They will be repeated after that. So this way we sample the frequency. Now coming back to the design, that there are two types of design. One is type 1 design and type 2 design. In type 1 design, the set of frequency samples includes the sample at frequency omega is equal to 0. In some cases, it may be desirable to omit the sample at omega is equal to 0 and use some other set of samples. Such a design procedure is referred to as type 2 design. So in type 2 design, we don't sample the frequency response at omega is equal to 0. So this part is taken from the book of Salivahan. Okay. Now, what is type 1 design? Let us say we only restrict to type 1 design. So we sample the frequency scale over 0 to 2 pi. It's 1 minute. So we take that discrete samples, okay, k is equal to 0 to m minus 1. So your frequency will also be discrete. Okay, so it is 2 pi, whole 2 pi frequency range is divided by m at kth number of points. Okay, so so there will be m number of samples. Now, so your so in place of omega, we should write omega k that is 2 pi k by m. Okay. Now this is, say, this is your discrete samples or discrete frequencies, okay, with magnitude hk, and frequency samples range from 0 to m minus 1. So this is in frequency domain. Now if you take the inverse discrete Fourier transform of it, so you will get h of n. Okay. Using the formula of discrete Fourier transform, that is 1 by m k is equal to 0 to m minus 1 hk into e to the power j 2 pi nk by m. This is the impulse response that we want. So, and this will also be your filter coefficients, and there are m number of filter coefficients since it will be a FIR filter. So m number of filter coefficients or samples will be there. Now, if these numbers are all real, then this can be considered as the impulse response coefficients of an FIR filter. Now, since you see exponential term is there, the imaginary term, so this number should be sometimes complex also. Hn may be complex, but actual filter coefficient should be always real. So there should be some there should be some manipulations, or there should be some manipulations or arrangements so that Hn should be always real. Now how it is done? So uh, mm, you see that this can happen when, so to be, in order to be real, the coefficients, this can happen when all the complex terms appear in complex conjugate pairs. So if you dissolve the series of this function, okay, this is for, say, for one particular value of n, let us say h1, so it would be 1 by m k is equal to 0 to m minus 1 h cap k h tilde k e to the power j 2 pi n k by m. So n is 1, and in this case k will vary from 0 to m minus 1. So for each particular value of samples of the impulse response, there will be some of the terms of complex conjugate terms, some of the terms which are complex numbers. But if those appears in complex conjugate pair, then we can say that the real part will exist and imaginary part will vanish, or they will cancel each other. So in order to happen, in order to have that concept, so what we do, uh, we just replicate the impulse response hk over half of the samples. So there are samples of hk, and k range from 0 to m minus 1. K range from 0 to m minus 1, and your samples is hk. Now, from the samples from 0 to 1 to m minus 1 by 2, okay, these samples will be repeated after so first half of the samples will be repeated at the second half of the samples. So that means, let us say, if there are values of k from 0 to 0 to say 6. Okay, say m is equal to 7. So k will be from m minus 1. So 7 minus 1, it is say 6. So 1, 2, 3. K 1, 2, 3. K is equal to 1, 2, 3. So for those values of k, what will happen? Hk first three samples. Okay, uh, first three samples would be what? H1, H2, H3, and next samples H4, H5, H6, they will be all equal to H1, H2, H3, but complex conjugate. So when we will multiply, so in the DFT term, this is multiplied with exponential term e to the power j. Their complex conjugate terms are there. Now, uh, so when they will all be added, okay, so overall we will get one real value. One real value we will get. So this is one concept I am not explaining, but here I have given some note that how it is being calculated. So this is the derivation of hn. Now how this is occurring? Okay, so how we get the, say, let us say one particular term h m minus k e to the power j 2 pi n m minus k m. Okay, now k may be any values, k may be 1, 2, whatever it is. So let us say it is say 1, or you may assume any value. Okay, so for any value, let us keep it to the variable h m minus k. So this is one term in the IDFT function. So this is actually, you can consider that this is coming from one particular term for k, hk into the power j omega n. So here we, in place of k, there should be some variable m minus 1 or m minus 2, whatever it is. Okay, so uh, so that value is this, and it is multiplied with e to the power j 2 pi n m minus k by m. So if you get that, if you see that this is actually e to the power j 2 pi n, if you split it, okay, e to the power minus j 2 pi k n by m. So this e to the power j 2 pi n is actually equal to 1. So this term h m minus k into e to the power j 2 pi n m minus k. So this is actually h m minus k e to the power minus j 2 pi k n by m. Okay. Now, uh, so in place of, so if you assume h m minus k is equal to hk, then what happens that h m minus k e to the power j 2 pi n m minus k by m is complex conjugate of hk e to the power minus j 2 pi k n by m. Okay, so this will cancel out each other. Okay, and it is actually it tells that h m minus k should be complex conjugate of hk. So this concept is used, and for two cases m odd or m even, this is implied. Okay, and finally what we get, that the equations of hn and for m all or m even is given using this formula. You should note down this formula. Okay, I have given here. So so these are the two main formulas for this frequency sampling method. Now let us see one example. Okay, so There are many examples I have kept, so I discuss only one here. So this example, a low pass filter has the desired frequency response as given below. So omega for frequency range 0 to pi by 2, it is hd omega is e to the power minus j3 omega, and pi by 2 to omega, it is actually 0 for all frequency range, and determine the filter coefficients Hn for m is equal to 7 using type 1 frequency sampling technique. So we just according to this graph, okay, here number of points they have assumed 17, but for our problem let us keep up to 6. Okay, so we should we should uh, divide using some zone, okay, for samples. So what is our frequency term? It is omega is equal to 2 pi k by m. Okay, omega k is equal to 2 pi k by m, and k varies from 0 to 6, that is m minus 1. So for the range given, omega is within 0 to pi by 2, which frequency points are coming? Okay. So the points are coming 0, 1. So that means 2 pi, that is 0 always there, and 1. 1 means 2 pi by 7. Okay. 2 pi by 7 means 2 pi by 7 is actually within pi by 2. 2 pi by 7. Actually, it is how much? So, it is whatever it is actually less than 2 pi by 7 is falling in the range of is less than pi by 2. So it is not 0. So we can use the as e to the power minus j6 pi k by 7, where m is what? It is 7, and k values range from 0, 1. So we get it as e to the power minus j6 pi k by 7. Okay, according to the function given, e to the power minus j3 omega. Omega is 2 pi, so it will be 6 pi, okay, by 7 into k. 6 pi by 7 into k. So for k is equal to 0 to 1, because for these values omega falls within this range 0 to pi by 2. Okay, then after that within pi by 2 to pi, okay, 0 to pi, so it is how much? It is 0, and again after so all these frequency points 2, 3, 4, 5, okay, 2, 3, 4, 5 actually falls within this range pi by 2 to pi, okay, pi by 2 to pi. So that means if you calculate, it is pi by 2 to 3 pi by 2. Pi by 2 to 3 pi by 2, we actually get the frequency samples 2, 3, 4, 5. And again it will be repeated after this 3 pi by 2 to 2 pi. It is actually the frequency range we get as k is equal to 6. Okay. So k is equal to 6, the frequency samples falls in this category. So we divide the zones of frequencies, samples, and now we write the actual frequency response. So for this samples 0, 1, it is actually to the power minus j 6 by k by 7, and for 2, 3, 4, 5 it is 0 as per the specification, and for k is equal to 6 it will be the same. Okay, so now use the formula, okay, of DFT IDFT. So if you use these values, you will see that it is coming to be this function. Okay, so you just go through it, practice it, and it is very interesting. Okay, and some other examples I have mentioned here for clear understanding, for more understanding. Okay, so now I stop here, and if you have any doubt you can ask. Okay, so now so today I stop here, and next class will be on Monday. Okay, on the fifth module, although very few classes are there. So and tomorrow is your exam, so don't forget it. Fourth quiz is tomorrow, from 6 o'clock, okay, or as per the notice given. And on 12th we have the fifth quiz or final quiz. Okay, so take preparation, and also tomorrow is Diwali, so celebrate it, have fun. So now you can leave. Okay.